Hi everyone, and welcome to part 9 of this formal logic video series. In this session we're going to complete our proofs in QL by adding in the final 4 rules. So that's the identity, introduction and elimination rules, the existential elimination rule and the universal introduction rule. Now I'm going to speed through the introduction and elimination rules for identity because I think they're pretty easy for us to pick up and not too difficult. The existential elimination and universal introduction rules tend to be referred to as the hardest rules that we look at in QL. I don't think they're actually too difficult if we think of them in terms of a structure that we can put into any of our proofs. So I want us to have a look at these structurally and not dwell on them being difficult, and hopefully just thinking about them as a structure or an architecture that we can use in a proof is going to make them seem a lot easier and a lot less daunting to use. Okay, so let's first of all whiz through these rules for identity, introduction and elimination. The introduction rule is really very simple. On any line at all, so let's have this as line M, we can just write, so for any constant that we want, so take A, we can write A equals A. And we'll just justify that with the rule identity introduction. Okay, so we could have written any variable there, so we could have written b equals b, and so on. Let's just make this a bit longer. So in general, if we take chi to be any constant or parameter, then we can always just write chi equals chi. Okay, so and it'll always just be, we don't need to cite any other lines because this is just taken to be a self-right. We know that for any particular thing it's identical with itself. Okay, so it's as simple as that for the introduction rule. For elimination, again, very simple. Suppose that we have the following formula. If we have, let's say, FA and GA, and we know that A equals B, then on any line below that, we can swap out one or all of the constants mentioned there. So we could say FB and GA, and that would be with appeal to lines M, N and the identity elimination rule, or we could have swapped out both of them, so we could say FB and GB, and again that would be M, N and the identity elimination rule. And it's really that simple. So if we've got an identity statement, let's formalize it in fact just a little more. So if you have on line M some formula phi which has tau as a constant or parameter in that formula, and we know that tau is identical to gamma, then on any line below that we can write phi gamma with an appeal to M, N and the identity elimination rule. And it's just that simple. Right, I don't want to dwell on it too much more because I think it's really obvious rule to use. The only thing to note is that in this formalization, obviously phi could be a longer formula, right? So phi could be a formula like this, FA and GA. We're just saying that tau is a variable within that formula. It's a variable or a constant or a parameter in that formula. Okay, so that's identity. Really simple, and I think everybody will pick up that very easily. And what I really want to concentrate on in this session is the existential elimination and the universal introduction rules that people tend to get a bit more stuck on. So let's take the existential elimination rule first, and let's start off with an example. So here's our scope bar, and let's suppose that we want to show that if we know that there exists an x such that fx, and we know that every x is such that if it has property f, then it has property g, therefore there exists an x such that gx. Okay, so hopefully we can see from this, look, there is something with this property f, and we know that whenever something has property f, it will have property g, so something must have property g, right? Because we know that something has property f, and this rule holds for all things that have property f. So this should work easily. Now our issue is that when we were doing propositional logic, what we might have done is just said, well, if we've got, let's draw a little scope bar here. If we've got A, and we know that A then B, then we can derive B, and we would just use our horseshoe elimination to do that, and lines M and N. It's just as simple as that. Our problem here is that, let's just write this out, so on line 1 we've got EX, FX, and on line 2 we've got every X such that if Fx then Gx. Our problem is that to use the horseshoe elimination rule, I mean, only if we've got a conditional phi then psi, we need the exact antecedent. We need phi exactly in order to derive psi. Now, our conditional, first of all, is kind of locked away by this. This is kind of this is like the main operator of this sentence. Remember that, albeit that they're not really like the other operators, quantifiers that are binding variables act a lot like the tilde symbol. So this is like the main operator of this whole sentence, and we can't get at this bit here to do anything with it until we've gotten rid of the universal quantifier. Now suppose that we did that. Let's suppose we did a universal elimination and we said, okay, well, let's just swap out the x variable, replace it with an a, and get rid of that universal quantifier. Okay, so now we've got the conditional statement on its own. It's not trapped or anything. Our problem is that we need this exact formula. Right? We need fa, and what we have is exfx. Okay, so that is not going to work to allow us to derive anything from here. So we're going to need to take a different route. And what we're going to need to do is an existential elimination. So the way we do that is to start a new scope bar. But this is a special kind of scope bar. This is a scope bar on which we're going to introduce a parameter. So let's say that we have on this scope bar the parameter u. Now u is a dummy name. It doesn't refer to it acts like a constant, but it refers to no constant in particular. It's like the name Joe Bloggs. We could say someone has a particular property, so let's suppose that someone is Joe Bloggs, see what follows from that, and then that what follows from Joe Bloggs having a certain property must be the case, right? Because Joe Bloggs is no one in particular, so we're kind of abstracting away from particular statements. We know that someone has this property, and then we look at what would be true of anybody who has that property and derive that. Hopefully that will make a bit more sense as we go through this. So the important thing to remember about this bar, at least, though, is that this parameter u can only appear on this side of the scope bar. Right, it cannot appear here. Okay, so whenever we write u, it must be on this side. Let's get rid of that. Okay, so in order to start this, as we're doing an existential elimination, we're going to start it with an assumption, and the assumption is going to mirror our existential statement. So it's got to mirror this. Let's make that look less like an assumption. It's got to mirror this here. Let's just mark that these are premises. So what we're going to do is eliminate the existential quantifier, and we're going to swap out all of the variables that was binding for our parameter u. So we're going to write f, that's going to stay the same, our property, our predicate, but we're going to change the x for u because we're on this u parameter bar. And that is an assumption that we're making. So we're saying assume that u has property f, where u is just this dummy name. Okay, well now, if we remember, the problem that we had before was that we could get our conditional on its own, and I'll do that here by reiterating up ax, fx, then gx, that's 2 reiteration, and then eliminating the universal quantifier to get f, and again I'm going to replace the variables here with my parameter. When we're on a parameter bar, in general it's always a good move to replace variables with the parameter that we're on, of the parameter bar we're on. That's going to be the most useful constant that we can, or it's not a constant, it's a parameter, it's going to be the most useful thing that we can replace a variable with on that parameter bar. Okay, so now we end up with fu, then gu, and of course these two match. So we're now free to derive gu. I'm going to need to make this a little bit longer. Okay, so we can show that gu and, sorry, this should have been 4, universal elimination, 6 comes from 3 and 5, horseshoe elimination. So it's just a normal horseshoe elimination we've done here. We had a conditional fu then gu, and we had the antecedent of that fu, so we could just derive its consequent gu. Remember that we wanted to end up with, at the bottom of our proof, we wanted ex gx. Now what that means is that we just need the end of this scope bar here to be that very formula. We need it to be ex gx. And of course we can get that formula just by doing an existential introduction on gu. So that's 6 existential introduction. Okay, so if we've got a scope bar that begins with an assumption that has been derived from some existential formula by removing the existential quantifier and replacing all of the variables that it bound with a particular parameter, if we show that that assumption, where we've made that move, leads to some formula that doesn't contain that parameter, remember the parameter can only be on this side of the scope bar, so we need to remove all the parameters, then we can just straightforwardly do kind of like a carriage return and just move it down and left onto our main scope bar. So line 8 we get ex gx, and that is going to be from the line that has the existential quantified statement on it, so line 1, and then we want to show a range, so we want to show the scope bar where we did all the work, so 3 to 7, and existential elimination. Okay, so there's more moves in here than there are in the other rules that we've looked at before, but they're all quite basic moves. The important thing is that we remember that for an existential elimination, I think the most important thing to remember perhaps is just that in order to derive a particular formula from an existential elimination, the scope bar needs to end with that exact formula. Right, so these two are identical, right? We've just picked this formula up from line 7 and just shifted it down and left to line 8, so they're exactly the same. And then the other thing to remember is that this scope bar must begin with an assumption that's modelled on the existential formula we're eliminating. So let's give a formalization of that, and then I'll work through another example so we can see it in a bit more detail. So for our formalization, let's just draw my scope bar. Okay, so if we have a formula e chi phi chi, so where chi is the variable of this formula, we can eliminate that existential quantifier by having a new parameter scope bar. So here it's a tau bar, so I'll use tau to represent the parameter here. That begins with phi tau, so where the formula phi chi, e chi phi chi, we've eliminated the existential quantifier and replaced every instance of chi with a tau in that formula. Then we'll put dot 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 here because somehow we get to a different formula at the bottom. Here I'm going to say we get to psi gamma. Right, so if we get down to some other formula, then we can just move that formula down here. And the important thing to notice here is that, let's put this in a different colour, it's not tau does not equal gamma. That's really important. Okay, so this variable here is not the same as our parameter. Right, we can't have a formula moving down and left from this bar that has the parameter in it. Okay, in fact, let's do this M, N, O, P. Oh, and that's an assumption, sorry. So assumption, it's not clear how we get to this, but we derive this formula from our assumption, and this formula has to involve no instances of our parameter tau. Then on this line we can have M, N to O, existential elimination. Okay, so we need to just bear this structure in mind. And I think one of the things really to remember, as I say, is that often the way we're going to come at this is we're going to be thinking, okay, I need to derive some formula. Remember, we're going to be looking at the bottom of our page and thinking, how can I get to this? Well, the thing to think is, if it's by existential elimination, so say we, whoops, let's get our line tool. You know, suppose we're saying, okay, we want to derive what's on line Z, and that's formula phi. You know, we might have some stuff up here. If we're thinking the way that we're going to get this, if we decide to try doing a existential elimination, then immediately what should become apparent to us is we're going to need a parameter bar which ends with phi, and where phi doesn't include that parameter. Right, so that's just something to bear in mind. Okay, I'm going to do an existential elimination. The structure above that, the stuff that I need that comes before it, is going to be this parameter bar ending with the exact same formula I'm trying to derive. I think that's a really important thing to remember about this rule and the way that it's going to work. And of course also we're going to need an assumption at the beginning of this to start it off. But again, I think because we're going to be working backwards a lot of the time, it's really important to remember that the end of our scope bar just becomes that we just move down and left from the scope bar, the parameter bar we were working on. Okay, so let's have a look at another example of that. Let's just do it down here. So suppose that we have, there exists an X and there exists a Y such that X has property A to Y, and we want to show that there exists an X such that there exists a y such that a yx. So we basically just want to take these two parameters and swap them round in order to get here. That's all we're doing. We're just doing a swap. Now we can do that quite easily using our existential elimination. And let's work through it backwards this time. So we know that we've got this premise ex ey axy, and we know that we want to get down to ex ey ayx. So that's our z, that's our end. That's what we're aiming towards, and we're going to do it by existential elimination. Okay, what that immediately tells me that I'm doing it by existential elimination is that here I'm going to need a particular kind of structure, and I'm going to draw that in straight away. I think it's really important to think structurally in this way, to think from the bottom and then filling in all of this gap. I'm going to need a parameter bar, so we'll have u as the parameter for this bar, and it's going to have to end with ex ey ayx. Okay, I just know that immediately because I know that if I'm doing an existential elimination, I have a scope bar, and at the end of that, whatever I finish up with, so long as it doesn't contain this parameter, it just moves down and left onto the main scope bar, or the scope bar to the left of it. Okay, so that's my line y. Again, now I need to think, how could I get this formula? Well, look, I've only got... Oh, and sorry, we can also fill in this top bit. Right? If we're doing this parameter bar, we can fill in the top and bottom, we can work in towards the middle. This is what we know it's going to end up with. It's going to be a existential elimination of this statement. So the main operator, or the kind of what's controlling this formula, is this formula here, this existential x. So if we're going to do an existential elimination, we have to get rid of that first. We couldn't do it on this because this comes under the scope of the ex. The ey is trapped just like the axy, so we can't actually manipulate it at all. So we're going to need to get rid of the existential x, so we'll end up with ey, and then we'll swap out the x for our u, because that's the parameter bar we're on, a u y. Okay, and that's an assumption that we've made to begin this parameter bar. Okay, now we need to get to ex ey. We can look down here again at the bottom. Again, look, the only things I've got to work with are these two existentially quantified statements. So it looks like, again, I'm going to be doing an existential elimination in order to arrive at that. The main operator that I've got here is so this is the only thing I've got to work with. I guess we could have thought, well, maybe I could introduce this. So if we've got, let's just write this out here, ex ey ayx, we could think, well, maybe I could do that by two existential introductions. Maybe that would be... So before that we would have had, there exists a y such that, and let's say we had a yb, and then before that we would have had just a, and let's use c, a cb. So if we could have gotten to a cb, then great, we would have been able to derive this through two existential introductions, but our problem was that we started off with this statement, ex ey axy, and there's no way of getting to this and turning the x into an a and the y into a b. Sorry, the x is a b, the y is a c. We've got no way of doing that. In fact, the only way that we can affect this is by doing an existential elimination and doing what we're doing here, replacing those variables with parameters. Okay, so this isn't going to work. right, this particular method, we're going to need to do it this way. So again, we're at a point where we've got ex, ey, a, yx. We could do the same thing here, right? We could have gone back to acb, or perhaps aub, something like that on this line, but we'd have no way of getting to this auy. We need to get rid of this existential quantifier, so we're going to do another existential elimination to get there. And again, what that tells me straight away, if this is an existential elimination, is that this parameter bar must end with ex, ey, a, yx. It just has to, because our existential elimination rule says that whatever is on this line is just going to move down and to the left onto the scope bar to the left of it. This scope bar is going to be another parameter bar, so let's use the parameter v here, and it's got to start with an assumption, and that assumption has to be the result of eliminating this existential quantifier, this ey, and replacing it with, and replacing all of the instances of y with our new parameter v. So we're going to end up with a, u, v. That's going to be another assumption of ours. Okay, now we need to get from auv down to ex, ey, ayx. And remember, we saw that if we had, over here we've seen if we've got a formula that's under no quantifiers whatsoever, we've just got a, c, b here, that mirrors this formula here, right, mirrors this one, auv. If we've got that, we can just do two existential introductions in order to get the formula that we want. And I think what we're going to do again is work backwards, because we need to get the quantifiers in the right order. Okay, if we do the x first, let's say if we did ex, a, and the x has got to go at the back, so it's going to be aux. If we do that, we're stuck, right? Because, let's just move that a bit higher. If we remember from the last session, whenever we do an existential introduction, the quantifier has to go on the front of that sentence. So we have to stick the existential x on the front of auv and change the v to an x here. If we want to do the y, then the y would have to go on the front. X, a, y, x. So although this part of the formula would be right, these two parts would be wrong. Okay, we wanted them the other way round. So that's why it's always better to work from the bottom up. So in this case, we know that we want to have ex, ey, so the x has to come before, the quantified x has to come before the y, so that just means that the previous step to this one had to have been the addition of the existential x, so we'd end up with ey, a, y, v. And then, of course, that just comes from auv. That would have just been a simple step. So let's fill this in. 2, 3, 4, 5. Get rid of our y and z, sorry. 6, 7. So 2 assumptions, and then 4 is from 3 existential introduction. 5 is from 4 existential introduction, and then these two, let's rewrite our rule so we've got a bit more space, are going to be 2 existential eliminations. So the first one is from line 2, and then lines 3 to 5, and then the second one is from line 1 and lines 2 to 6. Existential elimination. Okay, so again, think in terms of structure. As soon as we know what we're going to derive and that we're going to do it by an existential elimination, we can draw in our parameter bar, and if we've got the quantified statement, then we can begin that parameter bar with the assumption, the relevant assumption to that statement. Okay, and just something, just finally before we move on. Something to bear in mind. Quite like this little diagram I drew. If we've got a E chi, phi chi, when we go onto our U bar, or our tau bar, tau cannot ever be on this side of the scope bar, right? It can't come that way. Tau can only be on this side. Okay? So just bear that in mind with parameters, that we can only have them on the right hand side of the bar that introduce them. Okay. So there's our existential elimination. Again, I don't think it's as hard a rule as is made out sometimes. It's just a simple structure. We have an existentially quantified statement. We remove that quantifier and replace all of the variables that it was binding with a parameter. And we do that by assuming that formula on this parameter bar. Then whatever that bar ends with, so long as it doesn't have this parameter in it, we can just move it down and left. We'll just do a little carriage return back onto the scope bar that we started with. Okay? Let's move on to think about the universal introduction. So let's suppose that you know that every x is such that if it has property x, then it has property g, and you know that everything is also such that if it has property g, then it has property h. Well, from that, it's kind of a transitivity point to be made here, that quite obviously, if those two things are the case, then everything that has property f must have property h. Right, because if anything had property f, it would have property g. Just have this f to g and g to h motion. So we should really just be able to go straight from f to h. And it's just a straightforward entailment. So let's see how we would do that in a proof. So here's our scope bar. And I know that every x is such that fx then gx, not very good x, fx then gx, and I also know every x is such that if gx then hx, and I want to get down, here's my, let's put a little z here, I need to get down to every x is such that if it has property x, then it has property h. Okay, again we're going to need a parameter bar to do this. What we're going to do is just think, well, we'll introduce our dummy name, so this time I'll use u again. We want to say that if, because this is a dummy name, because it's no individual in particular, we can say that if something must be true of just about anybody, right? If something is true of anyone at all, so take our Joe Bloggs, right? If something's true of Joe Bloggs, our kind of imaginary no person, then it must be true of every person. So we'll start off with our parameter u, and again, thinking from the bottom up, if I'm doing a universal introduction here, the first thing that I can write, first thing I can draw is my scope bar, and then the first thing I can write, first line of proof, is the one before this. So in this case, it's going to be fu, then hu. Okay, let's change this parameter to a blue one so we can see, keep track of it. So at the bottom here, we're going to do the opposite step to that which we made in the beginning of our existential elimination. So remember, in our existential elimination, we go, say, exfx, and on our parameter bar, we take off the existential quantifier, so we get rid of that, and then we swap all the x's for u's. Okay, so we end up with FU, that assumption. Well, now we're going to do the exact opposite of that. Let's just move that out of the way. In fact, let's move it over here and look at it in a bit more detail. We're going to do the exact opposite. So here, if we have a parameter bar that ends with FU, we can turn it into a universal statement, so long as that parameter bar started in the right way. And we'll say a little bit about how that has to start. But the point is that the end is exactly the same. We add on, so we're going to sort of plus AX, that's going to be added on there, plus AX, and in that case we're going to swap out all of the U's in that formula for X's. So we drop it down into the left and we write AX FX. Okay, so it's just the reverse operation. That we're going to do. And as I say, as soon as I've decided that I'm doing a universal introduction, I can write in that final step, that penultimate step. This is what has got to have been here. In order to get to AX, FX, then HX, I needed to have a formula with this parameter in it that mirrors this one in that way. That is basically this formula where all of the variables are the parameter on this bar and it's lacking its universal quantifier. So I can just add on that quantifier and then change these parameters for variables. Okay? Now, how do I get to FU, then HU? Well, let's just think. How do we introduce a conditional? Let's suppose we're doing a conditional introduction. We need a scope bar that begins with the antecedent. In fact, let's do our U's in blue again so we can keep track of them. And ends with our consequent. So this is just going back a few weeks. This is just our PL rule, right? The rule that we looked at, the more basic horseshoe introduction. Exactly the same rule that we're going to use now to get FU, then HU. And notice that we can assume this here, so we can begin the parameter bar on which we're doing this universal introduction with an assumption, but the assumption can't possibly go here. Let's change to red. Right, we couldn't have an assumption here. And we'll look at that in just a second. The assumption, if we want to start it with an assumption, then that assumption has to go on a new scope bar. So we can start two scope bars simultaneously. One parameter bar and one new bar with an assumption on it. Okay, but the assumption must go there. So let's get rid of that. And I think, I have a feeling I might need to make this a bit longer, so let's just do that quickly. Oops. Let's move that down. And join them up. Okay. So we're just trying to get from FU to HU. But remember, we've got these two formulas to reiterate now. So if we reiterate up AX, FX, then GX, then we can eliminate that universal quantifier to get FU. Again, let's use our blue to do that. FU, then then GU, and from that, so that is, these are two premises, that was 2 reiteration. So from FU and FU then GU, we can derive GU on line 6. So that is going to be, oh sorry, this was for universal elimination, and that is 3, 5, horseshoe elimination. these two rules, did I? Then all we need to do on line 7 is reiterate up this second one. That's a reiteration from line 1, not 2. This is a reiteration from line 2. Every x is such that gx then hx, and we can eliminate that universal quantifier again to end up with gu then hu, and then just straightforwardly do a conditional elimination, a horseshoe elimination from 6. Should probably write these in as I go along. 2 reiteration, 7 universal elimination, and then it's 6 and 8 conditional elimination gives us hu. So then we just do our normal horseshoe introduction, conditional introduction. We've got a scope bar here beginning with the assumption that fu and ending with hu, so we can introduce fu then hu, and that's going to be 3 to 9 conditional introduction. And then we've ended up where we wanted. So for line 11 we've got ax, fx, then hx. We've just come from this, right? So we've just swapped out the u, all of the u's here, we've turned those into x's, and we've just added that onto the front, that universal quantifier, and moved it down and left. And the rule for this, obviously it's a universal introduction, we only need to cite one line, line 10, right? Just the last line of this parameter bar. Okay? So now let's give a formalization of that, and then we can have a look at another example. So, in fact, we'll give 2 formalizations because there's 2 ways, as I said, to begin these universal introductions. So, if we're trying to get to every chi is such that phi chi, what we need is a parameter bar. So I'm going to use tau to represent my parameter. Now the way I just did it there, just before, this bar began with a assumption. So we had the assumption, so let's say here we had psi, and that led us down to phi tau. Right, so there were some steps taken in between. The important thing to remember is just that on line m we had the introduction of a parameter bar with tau as its parameter and an assumption. Right, it doesn't matter what this assumption is, but that assumption somehow led us to phi tau, a formula with tau as its parameters. And then what we did was just to swapped out this, changed it for an x, and we added on we changed it for a chi, that's a chi not an x, and we just added on our universal quantifier onto the front to arrive at the end. Okay, so if that's m, and it's a bit messy here, m, n, o, all we need to cite is line n, and universal introduction. So I think this rule is a bit simpler than the existential elimination. We just need a parameter bar that ends with this kind of formula, right, where we've got a formula and a parameter in it, and then we can swap out the parameter and add a universal quantifier on the front. Again, the only difficulty is the way that it starts. So here we started with an assumption, but we could also, let's draw another one here, got a little less space. So supposing that we wanted to get to every chi is such that phi chi, then we could have had a parameter bar. So here we're going to use the parameter tau. Let's do our taus in blue just so we can see that they're nothing like this. not these other letters that we're using to designate the lines. So a parameter bar with tau on it, and we would have had to end with phi tau, and then we would have swapped out. I mean, the most important thing again is just this ending, right? That's always the same. We swap out tau for chi, and we add on, so plus our universal chi. Okay, so that's the final step. The other way we could have started it, other than with this, let's move that over so we can make these a bit more distinct. So that's just from n, universal introduction, and this mn. Oh, again, this would just be n, universal introduction. The other way we could have started it is with a reiteration of some formula. So here we'll have psi, and it's a reiteration. Okay, so there are two methods for starting the parameter bar for a universal introduction. We either have new assumption, right? So you have a new assumption on a new scope bar, right? So that's important. Or we can have a reiteration of a previous formula, so from up here. So phi would have had to have come from above. And it's important that we remember those two. So whenever we're starting, I mean, we can kind of draw a little table here to show us how our parameter bars start. Right, so we're not going to worry too much about their endings. Got three possible beginnings to parameter bars, and we'll just do ... here to show that they carry on to other things, bigger and better things. So if our, in fact, let's just draw on the rest of the bit more of a scope bar so we can see where it's going, see what we're doing a bit better. Okay, so if a parameter bar begins with an assumption here, then that's got to be for an existential elimination. Okay, that's the only thing that that can lead to. If it begins with a reiteration, so let's just show that that's an assumption. If it begins with a reiteration, it's got to be a universal introduction. If it begins with a second assumption on a new scope bar, so it's really important that we just point out this is a new scope bar. If it begins like that, again, it has to be a universal introduction. Let's just cordon these off from one another so we can see that they're three different ways of starting our parameter bars. And if we remember this, then parameter bars needn't give us too much bother. Right, we just need to ascertain, we already know how they're going to end. So an existential elimination ends, we need to end the parameter bar with the exact formula that we're trying to derive, whereas a universal elimination, we need to end it with a formula that's got the parameter in it for the bar we're on, and then we swap out that parameter and add on universal quantifiers, or just one universal quantifier. So just with the beginning of those scope bars, we just need to remember that if it starts with an assumption, if a parameter bar starts with an assumption, just straightforwardly, it's got to be an existential elimination. If a parameter bar starts with a reiteration of some previous formula, in fact we could draw that, couldn't we? Let's make our tau a little bit smaller. See, it's not supposed to sit on this bar. So phi would have had to have come from up here. And in fact, let's fill this in a bit more. So we could have had phi tau, and we would have had e chi phi chi up here. So again, it's just a case of moving that onto there as an assumption this time, or a reiteration. If we've got the scope bar beginning with a new scope bar and an assumption on it, again it's got to be a universal introduction. Okay, so those are our three beginnings to parameter bars. And those are the only three ways that they can begin. Right, so if we remember those, then we're going to be sorted. Okay, let's have a look at a second example of universal introduction. Okay, so suppose that you know that there's nothing, so there's no x which has property f, right? There's nothing that is f. Well, on that basis, we must know that everything is not f, right? Because nothing has this property. That means that everything that does exist must not have that property. Otherwise, there would be something that had it. So this is one of the quantifier equivalencies. Not ex fx is logically equivalent to ax not fx. So, how do we go about proving that? Well, we've got our first premise, not ex fx, and we know what we're working towards on line Z. We're working towards ax not fx. Okay, so how are we going to go about this? Well, one thought that we might have is maybe we should do some kind of, because we've got this existential statement up here, maybe we should try doing an existential elimination. Right, so we should have a parameter bar with a u on it that ends with ax not fx, because of course if we're doing an existential elimination we can just move that down and left, and if we, maybe we can get that easy enough on here. The problem is that this formula begins with a tilde, right? So we can't get at, because presumably we'd want to go up to here, something like fu, or even maybe we were thinking we'd have not fu or something like that. We just can't do that because of this tilde. Right, this negation is the main operator of this, so we can't do an existential elimination. The existential elimination is subordinate to that negation. Okay, so we're going to have to try it a different way. And I think that generally we should always try first just using the introduction rule for the formula, for the main operator of the formula we're trying to introduce. So here, this is kind of controlled by this universal x. Whoops. So, let's try and do it by universal introduction. So we can draw in, immediately we know that we're going to have a parameter bar, and it's going to end with, so let's say it's a u is the parameter for this bar, it has to end with not fu. Okay, so remember I've just gone kind of through the backwards process of thinking, if I've got ax fx, or okay, let's do it in terms of 5, we've got ax phi x, whatever phi turns out to be, whatever formula that is, I need to swap this for a u and get rid of that, and that will be the formula that led to it. Okay, so this is what is going to go down to there. So we know that we're going to need not fu. How exactly are we going to begin this? Well, we know that there's two ways that we can start this off. One way is to just reiterate not ex fx here. Oops, a bit clearer. Not ex fx. So that is a reiteration of 1. Let's do it this way this time, seeing as I started with an assumption the other time, and we'll look at how we start with an assumption in a second. Okay, now we just need to think, again, always be looking down, always look to the bottom formula, the one that you're trying to derive. This is the one we're trying to get to. How could I get not fu? Well, again, just look at what the main operator of this formula is, and let's try that first. Its main operator is a negation, so let's try to do a negation introduction. Negation introduction, if we remember, requires us to assume the unnegated form of whatever that formula is. So in this case, that's going to be, it's going to be fu. So we'll assume fu here, and then show that that leads to some kind of contradiction. So what can we do from here? Well, whenever we're looking for a contradiction, I think what we need to do is look back at the previous formulas that we've got. So in this case, they're both exactly the same, and think, okay, in this case we've got not ex fx. Look back at your previous formulas and think, what would contradict this? Well, the formula that's going to contradict it, remember when we're looking for contradictions, we need something like this. And we need the exact same formula, phi and phi, except that the second one has a tilde. Right, so one of them has to be negated. So in this case, we've got the negated form. What we'd want is ex fx. And these two would contradict. Let's just put contra. So let's reiterate up not ex fx from line, let's say from line 1, reiterate it up from there. Okay, we just need to generate ex fx, and of course we can do that really easily just with an existential introduction of 3. So fu just quite simply goes to ex fx. That's 3. Existential introduction, and there we go. There is our contradiction. These two are contradictory. So then we can write on line 6 our not fu, and that's going to be from lines 3, 4, and 5, and a negation introduction. And then we can finish off on line 7 with a universal introduction, and remember we just cite the final line of that parameter bar, so it's just going to be line 6. Okay. Now, if we look again at this, so I said we can start these parameter bars. If we're doing a universal introduction, we can start it with either a reiteration, which is what we've done here, or an assumption. We didn't really do anything with this reiteration. Right, this was kind of superfluous. We didn't need this because we just reiterated 1 on both occasions, right? So we could have just reiterated 1 up to line 4, or what it would have been line 3 if we didn't have line 2 there. We could have just reiterated this straight up here. So we could have begun our proof. Let's just quickly draw it in. Oops. Could have started our parameter bar off with an assumption. So, we knew that nothing had property f. So we could have just started off with the assumption that something had property f, and then gone, okay, that leads to ex fx. That's a premise. Assumption. That's from 2, existential introduction, and then just reiterated up not ex fx to get our contradiction. So on line 5 we get not fu, and therefore every x not fx. So that is 2, 3, 4 negation introduction, and 5 universal introduction. Okay, and again, it's really just, it's not, I think it's not as complicated rule as perhaps it first seems. When we think we've got parameter bars, we've got all this new stuff to think about. It's so much more complicated. It's really not. It's just a structure, again, that we can implement. And I think with both of these rules, what we need to do is establish, first of all, what is the previous line to what I'm trying to introduce. Okay, so first of all, so what is end of parameter bar? Yeah, so if we're doing an existential elimination, it's the same formula as we're trying to derive. Yeah, so if we're trying to get to phi, we need to end with phi. Okay, if it is a universal introduction, then it's the formula with parameters. Yeah, so in other words, we need, if we're trying to derive ax phi x, we need phi u. Okay, so what is the end of the parameter bar? And then after that, just establish what is beginning. So that could be an assumption, in which case it's going to be an existential elimination. It could be a reiteration, or it could be an assumption on a new scope bar. And let's just put that in red. New scope bar. A new scope bar assumption. And in both of those cases, it's going to be for our universal introduction. Okay, so those are the things to think about for this rule. What's the end of the bar, and then what's the beginning of the parameter bar. They both use parameter bars, right? And they're the only rules that we're going to use that on. So how is it going to end? And we can do that just by moving up from the formula that we're trying to derive, just as I've done here. I've looked at ax, not fx, and thought, well, immediately before that, I need this parameter bar here to end with not fu. How is it going to start? Well, it could start with an assumption or a reiteration. We've got both versions there. The version without the reiteration is a little quicker. And that's all there really is to these rules. So here's a formalization of all that we've looked at in this session. We've got the two easy rules, so identity introduction, we can just introduce for any variable or any parameter or constant tau, we can say tau is identical to tau, just citing the rule identity introduction. That's a very simple one. Identity elimination, if we know that phi tau and we know that tie equals gamma, then we can write phi gamma, and we can just cite mn and the two lines with first the formula and then the identity statement and identity elimination. That's a very easy rule, so we don't really need to worry too much about that, I don't think. Then the two other easy rules, of course they're easy, and we'll all get them. So existential elimination, if we have some existentially quantified formula, add all my brackets, e chi, phi chi, we introduce a parameter bar, so here the parameter is tau, and we change this, we remove the existential quantifier, and we change out all of the variables for that parameter. So we go from e chi, phi chi to just phi tau. Then through some manipulation we end up with a formula psi gamma, and we can just move that straight down and left onto our main scope bar, psi gamma. Remember that here tau does not equal chi and it does not equal gamma, so we can't move the variable tau, the parameter tau, from this bar where it starts. Right, we have to end up here with a formula that doesn't have tau in it. Okay. With the universal introduction, again we've got two ways to start it. The important thing I think to remember is that if we want to get to ax a chi, phi chi, we need our parameter bar. So here we've got a parameter bar beginning with some formula, here reiterated. So our tau bar, we need it to end with that formula with tau as its constant, or as its parameter, right? So phi tau will give us, if we add on a universal quantifier and change out the tau for chi, we get a chi, phi chi. And that could begin with a reiteration, or it could begin with a second scope bar with an assumption on it. Okay? So that's all of the rules that I want to go through for this week. And I just want to end up with, let's call it Chris's 5-step program for proofs. Okay? So, this is just for any time that you're stuck, right? You might look at the proof and just think, I don't know what to do. Okay, 1, look down. What are you trying to derive? Okay, so that's just this case of stop looking at what our premises are and just look at the conclusion that we're trying to derive, or wherever we are at the bottom, right? Whatever the formula is that we still don't know how we got to it. Okay, so look down and work that out. What is it we're trying to derive? Number 2, what is the main operator? Or the MO, let's call it. So what is the main operator of that formula we're trying to derive? Just ascertain that. Okay, now the fun part. 3, try to introduce via main operator intro rule. If that fails, try to eliminate from previous formula. And if that fails, our last ditch attempt is to try an indirect proof. Indirect proof, of course, is just where we assume the opposite, the negated form of whatever it is we're trying to derive, and then show that that leads to some kind of contradiction. And as I said above, when we're looking for a contradiction, look at the formulas you've already got and think, what is it that would contradict that? So if I added it's a case of just adding negations onto the front of those, and could we generate any of those formulas? And a lot of the time, proofs is just going to be trial and error. We're just going to have to give this first try and introduce it via the main operator introduction rule. If that doesn't work, okay, never mind, right, we'll just move on to try and eliminate it from a previous formula. And if that doesn't work, we'll try and do it by an indirect proof.